So random forests actually, which is similar to boosting. So boosting and bagging are also kind of ensemble learning techniques, and similarly random forests. So what exactly is ensemble learning is? It's essentially like the name suggests, it's an ensemble of one decision tree algorithm, right? So we looked at the diabetes tree algorithm and we came up with one model, a single model, okay? But in real world, typically the data sets are extremely complex, right? There are multiple concepts that are present in the data. So it's very difficult for for a single math present in the data, okay? And that's why in order to get good classification results or good regression or any other machine learning models, those one single model may not be sufficient. And in practice, you will need multiple models, each one capturing a different intricacies that are present in the data. This umbrella concept referring to having an ensemble of classifiers for a given problem in hand, okay? Just to give you a real world example, so I think we talked about this Netflix challenge, right? Which was there for a couple of years, about 3 or 4 years back. Basically, there's a company called Netflix, which is into like on-demand video, where you can watch movies and TV shows and whatnot on the internet. And as a user, you subscribe, and as you watch different videos, you can rate them as well. Basically, whether you liked it, whether you hated it, or you are okay with the movie and stuff like that. And obviously, they'll have lots and lots of data about the movies and the ratings, right? Given by many diverse set of users. By diverse, I mean diverse in their tastes. Some people may like documentaries, some people may like action movies, some people may like rom-coms and so on, right? So, and just like any other service, like Amazon, like Google, they also have some recommendation engine, okay? They have a recommendation engine, which is essentially, depending on your taste, depending on the ratings that you have given in the past, they will recommend you some new set of videos, right? And it's a recommendation problem, but still the concept of ensemble makes sense here also. So they came up with this challenge where they shared some data, and they said that they have some proprietary recommendation algorithm, and the challenge is that you have to come up with a better model which can give you better recommendations up to about 10% than what they have. And if you can reach the 10% mark, then you'll be awarded $1 million prize. Okay, that's the challenge. And finally, it was won by a couple of researchers from AT&T Labs. And in the final solution, they don't have just one model which beats the Netflix algorithm. Instead, they have like hundreds of models, not just tens or 20s, but hundreds of models. Each one, because each of these small little model is capturing a different segment of people conceptually, and different kind of corner case that is present in the data. Okay, so that kind of gives you a sense of the importance of ensemble learnings in real world analysis. Okay, and random forest is one such technique. Okay, at high level, it's very, very simple. So in the previous class, we learned how to build one single tree, a decision tree, whereas random forest, as the name suggests, it's a many trees. It's a forest of trees. Okay, but these forest of trees are constructed in a randomized manner, and that's why they are called random forests. Okay, and since it's an ensemble of decision trees, it's also called as an ensemble classifier. Okay, using many decision or ensemble models combine results from different models, and the result from an ensemble model is usually better than the result of one single individual model. That's obvious, right? One single model may not capture all the variations that are present in the data, and therefore for some records that model may be good, for some other records that model may be insufficient. Okay, and that's why you have a group of models to deal with that intricacies. Okay, built. So root node, you find what is a good splitting node, a splitting attribute. Okay, and for doing that, we computed entropy, we computed information gain for every attribute, and selected that as a splitting attribute. And then based on that splitting attribute, we recursively partitioned our data set, and then worked on individual partitions. So that's why it's a divide and conquer method, right? Now, I mean, you do compute information gain and stuff like that, but instead of focusing on all the attributes at every single node, you randomly select a subset of attributes. Okay, so I'm at the compute information gain for all the attributes that are present in my data. Okay, let's assume there are 100 attributes. So I compute 100 different values of giving the best value. Whereas in random forest world, I won't compute all the 100, but instead I randomly select a subset of attributes. Okay, that's a fixed number. It's a parameter to the algorithm. Let's say that number is 5 attributes out of this 100 attributes. Okay, and then I choose the best one among those 5 attributes. Okay, and then I split up my data set just like we did previously, and then we get individual subsets, and then we want to create a new set of splitting nodes, right? And at each randomly select a new subset of attributes, and then choose the best among those selected attributes. Okay, and that's why it's called a random forest, because you're doing this splitting node computation in a randomized manner. Okay, and since it's a forest, we just don't want to build one tree, but we want to build many trees. Okay, so the number of trees that you want to build is also another attribute, another parameter to the algorithm. When here, n is the, okay, let's go here. If the number of cases in the training set, so let's look at the second point first, just to cover what we just talked about. If there are m input variables, that means m attributes in the data. Select a very small number of attributes at every node in randomized fashion. And that number is given by small m, okay, which is the value that is input to the algorithm. And you select those many attributes at every internal node, and then choose the best among those selected attributes in order to find the splitting. Little m is kept constant through the entire algorithm. That means at every node, I choose the same, not same, but I choose exactly 5 attributes at random if my m value is equal to 5. Okay, that's the second part. That tells you how to build a tree in a randomized manner. And then algorithm, which is the number of trees that you want to build. Okay, and apart from, for every tree, entire data. Okay, instead, I randomly select some rows and then build a decision tree on that randomly selected data set. Okay, and that's the first part that is talking about. So cases is essentially the number of rows, observations or records. Okay, let's assume in the initial data set, my number of rows is equal to n. Now, instead of feeding this entire data set to my decision tree algorithm or the one of the random forest, I basically sample with replacement n times. Okay, that means I am again choosing n records, but with replacement. So, do you guys know what is with replacement and without replacement? Or rather, sampling with replacement, sampling without replacement. Yeah, so let me just quickly cover what that means. Yeah, so sampling with and without replacement. That's what we are looking at. Okay, so we all know what sampling is, right? Sampling is essentially you have a data set and you want to select a subset of records. Okay, that's sampling in a randomized manner, obviously. Now, there are two ways of selecting those subset of records. One is with replacement and one is without replacement. So let's say my initial data set has 4 values. Okay, 1, 2, 3, 4, actually 5 values. Okay, now I'm asked to select a sample. Okay, generate a sample of size 3. Okay, that's my problem. Now, in a without replacement world, what do I do? So I want to select three values at random, right? So out of my 5 values, I randomly select the first value. Okay, let's say that is 2. Okay. Now, what does without replacement tells you is that now that you already picked 2, you will remove that 2 from your data set. Okay. Then that means my data set will now become 1, 3, 4, and 5. That means the value that you pick for the second time will be from these 4 values, not from all the 5 values. Okay. So you are kind of so what does that mean? You can pick each value only once, right? Because once you pick it, you are removing it from your data set and you are picking the next value from this new data set, so to speak, right? So there's no way you can pick the same value multiple times, and that's why it's called without replacement. You're not replacing the data point that you just picked. Okay. Now, when I pick the next time, okay, first I picked 2 and my data set has become that. Now, let's say I picked, that's my first value, and let's say I again randomly select a value, and let's say that is 3. Okay. Since we are in without replacement, I remove it from the data set that we have so far. So now it becomes 1, 4, 5. And now I select again another value at random, and let's say it's 5. So it will become 2, 3, 5. And my data set will now become 1, 4. Okay. But I'll stop here because I just want to generate a sample of size 3. Okay. So now I have a sample of size 3 where each value is selected at random without replacement. Okay. Because we did not put it back into the set. Now let's contrast that with replacement. Okay. Here also, first step, you randomly select a value, and let's say it's 2 again. Okay. Now, unlike in without replacement, we will put back the value that we just picked. So my data set will still be 1, 2, 3, 4, 5. Okay. So I pick a value, I select a value, I put it into the sample, but I will not remove it from the original data. That's why it's called like replacement. So you're replacing the picked value back into your data set. Okay. Now, when I select another value next time, let's say it can be 4. Okay. Even though I selected 4, I will not remove it from the data set. So my data set will still be 1, 2, 3, 4, 5. Now, when I select it next time, I might get 2 again, right? Because I have 5 values. And I'm picking a value at random, and that might as well be 2, right? So actually it's 2, 4 because that's what we selected so far. And now we have 2 again, and my data set will still be 2, 3, 4, 5. Oops. Okay. So obviously, since we are doing with replacement, a single value can be chosen multiple times. Okay. And that's why, like in this case, we are getting 2 multiple times. And if I want to select next one, here I will not select like that because my sample size is only 3. But let's say if I ask you for sample size 4, then when I pick for the next time, I might get 2 again, or I might get 4, or I might get some completely new number. Okay. That's essentially the difference between with replacement and without replacement. So whenever I say with replacement, all I need to remember is a single record can be picked multiple times in the sample. Whereas in the without replacement, a single record can be picked at most once. Before it will never have a chance to get it again. Okay, is that clear? And there are a lot of statistical properties of each of this technique. Usually when we talk about sampling, we think in our mind about without replacement, but with replacement also has a lot of statistical properties. Okay. Now, in our going back to our on random forest, here given an input data set or training set containing n records, we sample n records again at random but with replacement. Okay, if it's with and similarly, even in bootstrapping, actually you use sampling with replacement. Okay, but keeping the boosting aside, for random forests, given a dataset size of n, we select n records again, but with replacement. Okay, so it might be possible that some records will appear multiple times, and some records may not even appear in the sample. Okay, now once you select that n records at random with replacement, you go ahead and build a tree on that particular selected sample of data. And then, like we discussed, we build a tree also in the randomized fashion by selecting random subset of attributes at every node, and then selecting the best among those attributes. Okay, so this way you construct one tree, and then you go back to your original data, generate another sample of size n at random with replacement. You get another data set, you train another tree, you build another tree using the same randomized mechanism, and you keep repeating until how many trees that you want. Okay, so that's the high level algorithm for random forest. Okay, and one subtle thing that you need to notice here is that, so in the second stage, second step here, while you are building the tree for a single sample, the random subset of attributes that you select will not be constant across every tree. Okay, only the number of attributes that you select is constant across entire algorithm, but the exact set of attributes that are selected may vary for every node. Okay, I hope that's clear. So let's say I'm selecting small m is equal to 3, okay, and my capital M is 20, let's say. That means I have 20 attributes in my data, and while I am building an individual tree in the random forest, I want to use 3 attributes at every split point. Okay, I'm at the root node. I randomly select 3 attributes from the set of 20, and let's say I got 1, 5, and 10. Okay, these are the 3 attributes that I randomly selected at the root node. Now I choose the best among these 3 values, 3 attributes, and let's say that best attribute is 5. Then I split my data set on that 5th attribute. I get individual partitions of the data. Now when I select splitting attribute for each of my partition, I generate a new set of attributes of size 3. Okay, so I will not use the exact same 1, 5, 10 that I used in the root node. Okay, so instead I generate another set of 3 attributes. This time I may get 2, 7, and 20 and 15. Okay, so first time we got 1, 5, and 10, and now for an individual partition, after you split on the root node, I might get 2, 7, and 15. Okay, so the subtle thing to remember is the number of attributes that you're selecting will be constant across the algorithm, but the exact set of attributes that are being analyzed at every node will not be constant. They may be varying because you randomly select again and again for every node. Okay, is that all clear? So it's hard to see why this will work and why this should give me a good result. Let me put it on the slide, that way it's kind of maybe it will help. Oops, okay. What is that? So okay, let me take an example here. Okay, so I have my data set which has 100 rows and 20 columns. Okay, not 100, but let's say 1000 rows. Okay, so my n is equal to 1000, and then m is equal to 20, and I give okay, let's say my input parameter little m is equal to 3. Oops, equal to 3. Okay, that means I am choosing 3 attributes at every split point. Now my first tree. So for constructing the first tree, I select a random sample n1 of size 1000 again, but with replacement. Okay, this is all clear. There's no confusion until this point, right? So for constructing the first tree, I construct a sample of size 1000 again, which is same as my input data, and I'm calling that actually let me call this sample as S1. Okay, now our job is to build a tree using S1 as my data set. Okay, I pretend that S1 is my data set. I build a random tree, not just a regular decision tree, but a random tree. So how does this work? How does a random tree gets built? First, I select m attributes from set of all attributes. Okay, set of all 20 attributes, right? And what is m here? 3 attributes. Okay, so I randomly select 3 attributes from the 20, and let's say those are attribute 1, attribute 5, and attribute 7. Okay, then I choose the best among these 3 attributes. Okay, and let's say that one is A5. Okay, so what is the meaning of best attribute being A5? I split my data set, which is S1, right? So our data set is same as our sample that we generated. So I split my data set on A5. Okay, that's my root node. So I just constructed the root node of my first tree. Now I get, let's say, 2 subsets. That means 2 partitions. So the tree gets into 2 branches. Okay, let's say that's called S12 and S22. Okay, now how does the decision the tree algorithm works? For each of this subset, we construct a tree. We construct a splitting node again, right? So now our goal is to split S12. Okay, so for S12, now we again select m attributes. Okay, so we don't use this A1, A5, A7 anymore, but we generate a new set of attributes. Okay, and this time they can be A2 or A5 again and A15. Okay, let's say these are my 3 attributes. Now next time we choose the best among these 3. Okay, we choose the best among these three, and let's say these are called A15. Okay, that's possible, right? That means I split my data set S12 on A15 now. Okay, and then I get another, we get new partitions of the data. Okay, and at the same time, we will also split S22. Okay, and for splitting, we again select M attributes, and let's say this time they are A11, A20, A18 or 17. Okay, and then we again choose the best, and let's say that is A17. Okay, you keep repeating that. So by this time, the tree that we have is essentially at the top we have A5. Okay, and how do I write this? And then in the bottom we have A15 and A17. Okay, this is my tree so far. And then similarly, just okay, that's my tree so far. And then similarly, I'll break A15 further, A17 further, and so on, right? So this way, I'll construct my entire first tree. Okay, now end of first tree. Okay, now we will go back to our original data set and then build a second tree. Okay, and how do I build a second tree? I again get random. Okay, let me continue in the next slide. So how does my second tree works? I again construct another random sample of size 1000, and let's say this is S2, not S1 but S2. Now our goal is to construct random tree on S2. And how do I do the random tree? Just like here, we select again M, come on, M attributes out of 20, and this one I may get A2, A7, 6, A9. Okay, it can be anything. So you continue this way. So as you can see here, the only thing that is staying constant is the value of M. That means 3. So all I am saying is I randomly select 3 attributes, but the exact values of those exact set of 3 attributes will change from step to step. Okay. Okay, so that's the random forest. Now, if you think about it, it's very, very kind of, you can't find intuition here, right? Why should it do better? I'm just doing random things at random time, and why should it become more efficient or more beneficial to build a classification model? So there's enormous theory behind it. Actually, there's a complete area of algorithm called randomized algorithms. There are many books also on randomized algorithms, and many of those it's very hard to find the intuition that we usually train for. So I cannot express why it will work in like 10 minutes or so. You need to look at the proofs and stuff. So let's just ignore that proofs, and let's just believe in the guy who introduced this, and let's assume it will work. Okay, and just for people who are curious, this is introduced by a guy called Bremen. Okay, if you search for that name and say random forest, you will, if you do type that in Google, you will come up, I mean, you will be given the original research article that he wrote, and there will be many others also, obviously. Okay, so let's go back to our R and let's see how do I build a decision tree. So again, I'll share a code snippet like this for your purpose. It's already there, I think, but I'll show you whatever I create as well. That way you have both. Now, random forests, again, just like any other thing in R, they have to be implemented in some package, and you need to know what that package is. And random forests are implemented in a package called random forest. Okay, and the first thing that you do is install packages random forest. Okay, I think it's already installed on my machine, but it's trying to install it again. Fine. Okay, and once I install, I'll load it, right? Library random forest. Okay, see the capital F. That's important because R is case sensitive. Okay, I do library random forest, and I can start using the methods in random forest. Okay, and again, to construct a random forest, there is a function in this package which is again called random forest, not surprisingly. Okay, and we already know that by putting question mark, we can look at the help of that particular function, and this is a function. Okay, it takes a bunch of things, but the important ones that we want to know is the data set size, and also a couple of these parameters like mtry, which is the number of predictors sample for at every splitting point. Okay, this is the value of little m. Okay, the small m value that we selected here, that you can provide, which is mtry, and then ntree is the number of trees that you grow. Okay, those are the two important ones. You can look at all the others also, which are kind of not required for an initial encounter with random forest, but you can look at them as well. Like you can look at how do I specify the importance of different attributes, and how do I, so once you have these many trees, whenever you want to do prediction, okay, you probe each tree to find the class label for that given test record in each of those trees, right? So for every training record, for every testing record, if I have 500 trees, then I get 500 predictions, one from each tree, right? Now, how do I choose the final class label for this particular test sample? Out of these 500 values, one easy way is to basically look at the majority and then call that as my final label for the test record. Okay, so you do some kind of a voting mechanism, and there are many other ways, and these are some of the things that you can kind of control by other parameters. Okay, so just like in the last class, let's read that what was that data? Diabetes data, right? So where am I for now? Get WD. I'm in some random place. So set WD C. Okay, I forget what that directory is. So let me go here. Module 5. Diabetes data. Right, this is what we want. So let's copy that. Okay, let me increase the font to start with. Okay. Okay, I need to change this to unique style. Okay, now I can say d is equal to read.csv diabetes.csv header equal to true. Okay, this we have already seen. Now all you need to, so in the last class we looked at how to invoke a decision tree using this rpart mechanism. Let me increase the font here as well. Right, so this is what we have seen as in the last class, the rpart function and the formula which tells you what is the independent variable and what is a dependent variable, and here class variable is a dependent variable, and we are using all the other attributes as the predictors, and that's why we give a shortcut as dot, and the data set and some parameters that you can give. Okay, and similarly we will have a function called random forest. So let's run that, which is here, you see that, right? So my random forest rf is equal to random forest. Just like in decision tree, we give a formula again. So class dot variable, which is a dependent variable, is a function of all the other attributes. So that's why dot, and my data is equal to d. Okay, that's my data set, and then I can give my mtry equal to, let's say, 4, and then my entry is equal to, let's say, 400. Okay, so I'm building 400 trees, and at each point I'm using 4 attributes. Okay, and that's it. I have my random forest. We can see class of rf. Oh, sorry, not. Okay, random forest. And you can also see the structure of random forest. There are many attributes that are already provided for you. The predicted values, error rate, confusion matrix, and the voting information. And then just like in decision trees, we have looked at attribute importance, right? I think it's called this one. So in the decision tree object, there's a attribute called variable importance, which tells you what is the ordered list of attributes according to their importance, right? Which is computed via Gini index, some measure that is used in this particular algorithm. Okay, and similar to that, we will have importance from decision tree perspective as well, and other values that you are provided already to the algorithm, and there are many others. Okay, so you can see rf dot confusion, which will be the confusion matrix. Okay, this we have talked about in the last class, and then similarly there's a importance. So here also, if you remember, even last class we found glucose level and body mass index to be important attributes in decision tree, and that's the same thing we found even in random forest in this particular case. Okay, so higher the better. In the random in the decision tree case, we got these values in a sorted order, whereas here they are not sorted. Okay, so that's as simple as running a decision tree gets. Okay, so yeah, these are some other. So one point that I haven't covered is essentially, so in the last class we talked about cross validation, right? Which is essentially like a way to measure the robustness of your your classification model, right? Remember, we divided the data set into k equal parts, and then we created different combinations of training and testing data sets, and then we tried using the same model on each of these different combination of training and testing data sets. Okay, and that's the way we kind of came up with a nice way of measuring the performance of our model. Okay, whereas in random forests, you don't really need to do cross validation. The way it happens internally itself kind of does similar things. So the algorithm that we covered before is kind of slightly incomplete in the sense that once you construct the sample set N1 or S1, S2, you divide into training and testing splits, and then train your decision trees, individual trees or random trees. Okay, so that's the features of cross-validation are kind of built into the algorithm of random forest, so you don't really explicitly need to do cross-validation. Okay, that's all this one says.